I want to go back over some of these slides to readdress some of these kind of definitions. So when we talked about Bronsted-Lowry, we said there were two reactions. We had acid and we had base. Right? What was the definition of an acid? Right? And proton was a misleading term. What we were talking about is H plus, donor. And then a base would be a H plus acceptor. So if we were to go through and look at, say, a really, really simple chemical reaction, let's actually show a little bit more of the bonds. I'm going to do it like this. H bond Cl. Sorry, I swear I'm not being nitpicky with where I want things. H bond Cl, and we'll look at Na bond O bond H. Okay, and we want to react these things. So theoretically, there's a plus sign in there. One of the very first things that you'll find within OChem is we ignore pretty much all the operators. We get rid of those plus signs. Those plus signs can be very misleading because they could confuse us with charges. And we're not trying to show charges, we're just trying to show that those two things react with each other. So if we were to predict the product of this chemical reaction, what would the product be? This is something that you should be able to do from your Gen Chem classes. If you can't, that's okay.
NaCl plus H2O.
Na bond Cl plus, and H2O isn't necessarily bad, but I'm actually going to write it as H bond O bond H. Okay. So from Gen Chem, and I already brought in that plus, I blame the Chem 130 class just got out of. You're supposed to be able to predict that as a neutralization reaction. It's effectively a double replacement, so all of that is stuff that you're supposed to have done in Chem 130. Okay. We start with it in OChem to go back to those definitions and really kind of push on what they're doing. Our acid donated protons, so HCl donated H plus to this thing. That's its goal. Okay? Do you see H plus in this molecule?
Yeah. I see an H.
I see an H. Is it H plus? No. Is it partially positive?
H.
Yeah. To make it formally positive, what would have to happen?
The electrons would have to go to...
The electrons in that bond all have to move to the chlorine. Okay? And if we're going to talk about it as a chemical reaction that this is going on, if we look at the end result, that bond doesn't exist anymore. I don't have a line connecting the H and the Cl. So let's go ahead and start using curved arrows to explain what's happening. The electrons in that bond need to go to the chlorine. Cool. That gets me my H plus. That's setting up my acid donor, my H plus donor. Okay, what's happening with the NaOH? The NaOH adds a couple layers of complexity to it. First layer of complexity, it's unique and different from the HCl. How? Sodium is a metal. That means it has an ionic bond, which means when we're looking at that, I don't see just Na, I actually see legit Na+. For HCl, I couldn't see H+. I could see it starting to form because chlorine was more electronegative. But when I look at NaOH, it should scream at me that's Na+. And if that's Na+, what happened to the oxygen? It took the electrons, which makes it OH minus. Well, if it took electrons, we should now account for the presence of those electrons. This would be going back to good old Lewis theory, or not Lewis, well, yeah, Lewis, our Lewis dot structures, and acknowledging that there's electrons already on that oxygen, and we took those electrons out of that bond, and the oxygen now owns them. Okay? What is something you remember about Na plus or sodium ion from Chem 130? We'll just see. Or if you took 151 or 152, you for sure talked about it there.
That it likes to get rid of bonds
Yeah. Word I'm looking for begins with an S.
Salt?
Spectators.
Oh.
Sodium ions are spectator ions, meaning when they run in a chemical reaction, they don't do anything chemically. Okay, and we'll come back to that in a second because we showed it over here in technically a chemical bond, but we'll address that in a second. Right? So our primary focus of concern with that sodium hydroxide isn't the sodium, it's the hydroxide. Well, what part of that hydroxide am I concerned about?
The H.
Okay? There's a lot of parts there. Which of those parts do you think is most relevant to be concerned about?
The negative charge on that.
Why the negative charge?
It wants to go to something.
Charge is inherently unstable. It needs to be neutralized. To be neutralized, it needs to go to something positive. You're absolutely right. So what I want to do is explain where those electrons are going to go. Well, where are those electrons going to go? They need to find something positive. Did you just establish that there was something else positive in the reaction?
The H and HCl.
The H from the HCl. So I'm going to take those electrons and I'm going to share them with the H. What happens in this system? So now we can go through and try and do some fun color coding. The bond between the sodium and the chlorine, actually I'll leave as black for the, nope, I'm going to leave it as, I'm going to make it purple. Okay, and the bond between the oxygen and the hydrogen will show as black to represent the black connection out over here. Okay, we still have the oxygens, 2 lone pairs. Okay? Next things to kind of push through. If we were referencing this as a chemical reaction, how do we know we have a chemical reaction? All the way back to Chem 130.
That what the names of them? The beginning thing is different than the end thing. That was awful.
That's a little too vague for me. I don't think I can accept that.
The products are different from the.
How? What's that?
What?
A precipitation? What's a precipitation?
A solid.
There, and it's not just the formation of a solid. It's a formation of a solid from
Liquid.
species that were not solids. So we know we have a chemical reaction if we have the formation of a solid, or the formation of a liquid, or the formation of an aqueous, or the formation of a gas, as long as that formation was not something that we started with. Okay, so it's a change in phase. That's an important thing. So if we think all the way back to Chem 130, you go, okay, well, how do we know changes in phases? This is where we deal with solubility rules and all that glorious fun nonsense. And if we were to go through and push all of those, what we would find is sodium hydroxide is aqueous. Hydrochloric acid is aqueous. Sodium chloride is aqueous. H2O is, it is not aqueous. It's a liquid. What does aqueous mean?
Soluble.
Dissolved in water. You really want to use water being dissolved in water.
No.
That doesn't make any sense. That's silly. That's because we would better define that as liquid. Okay, so now when we look across the chemical reaction, do we get a change in phase? Yeah, we did. We went from aqueous to liquid. That's a change in phase. That shows a chemical reaction. Okay, back to our sodium chloride. I said it was a spectator ion. We didn't need to really worry about it. Okay, it's aqueous, which means this species dissociates into the ions. What happened? The electrons in that bond sat on the chlorine, making the chlorine negatively charged and our sodium positively charged. What happened to the sodium through the course of the reaction? Started at sodium ion and I ended at sodium ion. It did nothing. Okay? So our metals, almost universally, we ignore. As soon as we see them, all we're really using them for is to identify that whatever they were drawn next to has electrons. Delete the metal. Okay? So I could delete that, and I could delete that. Can I delete the Cl minus? I mean, I got rid of sodium. Why can't I delete the Cl minus?
It's more important.
What kind of bond is between the H and the Cl? That's a polar covalent bond, not an ionic bond. When we look at the product, it's lost its bonding pattern. We can't just delete it. That's part of our kind of reaction cycle. Kind of makes sense? If we push through what we went through and did, we said our H plus donor. Okay? We didn't see H plus. We didn't see H plus until we took those electrons and we gave them to the chlorine. Should chlorine have taken electrons away from the hydrogen? Why? What's that? Yeah, chlorine's more electronegative than hydrogen. It makes sense to take those electrons away. Okay? This whole presumption effectively started with not looking at H+. We were trying to find it. It didn't exist until we moved electrons. Right? Well, then this definition's a little bit weird because we're trying to find H+, and H+ isn't there until I address how the electrons move. Okay? So talking about the movement of an atom is a pretty piss-poor definition. It doesn't allow me to actually see what's going on, because I never see H+. Okay? It doesn't come into existence until I move the electrons. And that's effectively what Lewis went through and did. And Lewis said, okay, these definitions are a little bit strange. I don't want to look at the H+, the presence of my atom. I want to look instead at the movement of my electrons. I still have acids and I still have bases. But instead of atoms, I want to talk about my electrons. Okay? So the easiest one to define is our base. Okay? And it turns out that our Bronsted-Lowry base will be the same as our Lewis base. What did the base do in the course of this reaction with its electrons?
Donated them?
Yeah. Our base was an electron donor. The base donated electrons towards the hydrogen. What does that mean the acid had to do?
Had to accept electrons.
It was an electron acceptor. So when we talk about OChem, most organic chemistry will center on this system of Lewis acids and bases because they're broader definitions. It allows me to step outside of the very narrow, I would argue, Arrhenius definition of acids and bases that we have up here as an example, and now allow me to use any organic molecule I want and look at how the electrons move around within that molecule. That's pretty cool. Okay? The problem with the Lewis acid definition is it is way too broad. It literally applies to everything. So we could go through and call something a Lewis acid or a Lewis base, but that doesn't narrow down the chemistry associated with it. Okay? So I don't like referencing Lewis acids and bases. Okay? I want a little bit more nuance behind it. So when I talk about acids and bases, I'm explicitly talking about Bronsted-Lowry. Because in those particular reactions, the only thing I'm concerned about is the transfer of a hydrogen ion. How it happened was still doing Lewis, moving electrons. But the only thing that really mattered was the transfer of a hydrogen atom from one place to another. Okay? Other reactions, I can't call Lewis acids and bases because the Bronsted-Lowry also sticks with it. So I need a new term. So the term that usually gets adopted is that we will then reference, make sure I tie them correctly, electrophiles and nucleophiles. Electrophiles and nucleophiles are Lewis acids and bases, just like Bronsted-Lowry acids and bases are Lewis acids and bases. But electrophiles and nucleophiles are not Bronsted-Lowry acid bases. Right? And this is where we have to be a little bit more nuanced within our definition. An electrophile, just like a Lewis acid, will accept electrons. Okay? So it is an electron acceptor. And a nucleophile, just like a Lewis base, is an electron donor. I'm using the exact same definition for both. So what's the difference? If I'm looking at transferring electrons back and forth between molecules, the electrons that are being transferred back and forth cannot be applied to protons. Cannot be applied to H+. Okay? That's it. So what we're going to end up with is now 4 names or 4 reactivities. So when we look at a molecule, we want to be able to say, is that an acid? Is that a base? Is that a nucleophile? Is that an electrophile? There is overlap. A nucleophile donates electrons. What does a base need to do? Yes, proton acceptor, but how did the base act as a proton acceptor? What did it do? It donated electrons. This is going to create a problem. Bases and nucleophiles directly relate to each other. They're acting the exact same. And if they're acting the exact same, it can be difficult to nuance what your species is doing. Okay? That strict definition line is going to be what's it reacting with. If I have an electron donor that's donating to an H+, my electron donor is defined as
An acid. Wait, sorry, go ahead.
if I have an electron donor that is donating electrons to an H+, that electron donor is by definition a base. It is donating its electrons to H+. Can't be our nucleophile electrophile because those specifically say not H+. There is a frog sitting in my throat. Get it out of there. What if I have something that donates electrons to a carbon? If I have something that is donating electrons, electron donor, but to carbon, that's not hydrogen. It's now a nucleophile. So differentiating my nucleophile versus base is going to come down to what am I reacting with. So I can't just look at one molecule, I have to look at the second to see how it aligns. Acids and bases will be a little bit easier, because what are the acids going to do? H+. Sorry, acids versus electrophiles. Acids will be H+. Electrophiles won't. Right? So I can very cleanly look at the structure itself to identify it. So when I ask for reactivity, those are the 4 things I'm looking for. When I look at a molecule, and we'll get rid of the Lewis, we're looking at acid, base, electrophile, nucleophile. And every time we want to run a reaction, what we want to do is identify those species. Oh, that's acting as the acid. Oh, that's acting as a base. Why do I want to do that? If I look at it and go, oh, that's acting as an acid, what kind of chemical reaction did I do? An acid-base chemical reaction. And I've compartmentalized what's happening in that reaction. That's nice. Okay, that's cool. If I look at it and I go, well, it's not involving hydrogen, well, now it's a different chemical reaction. Okay, what does it mean if it's a different chemical reaction? Well, that, of course, then means what do we need to learn? The other chemical reactions. Kind of, sort of. Okay, I believe we've got a video now where we talked about the 5 chemical reactions. Am I wrong on that?
Not if it's...
I'm seeing some faces, so I'm going to say no, I don't have that video yet. I'm not quite sure I believe that, but it's okay. We'll come back to those in a second. So, if we're now going through and looking at this, what can we do? Is that a question? Or you just, yeah, go ahead.
I don't really get what you mean by not voting.
How do I go to the next question? Active is weird. So let's look at an example. I want to run this reaction. Okay? We've got some limitations that are just kind of visibility things. Okay, so we are very clearly going to be reacting this giant thing in this box, right? What are we reacting it with? Okay, this very, very, very tiny thing down here that's hard to see. So let's make that bigger. We're going to react it with NaCN. What do you see? You see no? A metal. Awesome. So what does that metal mean? Okay. Cool. I've now found a negative. What does that negative need to react with? Something positive. So what do I have to find in the red box? Okay. How do things become positive? How do they lose electrons? When we looked at HCl, we said that that H lost electrons to the chlorine. Why did chlorine take the electrons away from the H? We were able to predict that reactivity because we saw a large difference in electronegativity due to effectively being a polar covalent bond. Awesome.
There's not a huge difference between C and O.
There's actually a very large difference between C and O. Oxygen is the second most electronegative element on the periodic table. You bond oxygen to anything, it's taking electrons away. Okay? Almost anything. We won't bond it to fluorine, so that kind of takes it away. What does that mean? There is a difference in electronegativity here. Oxygen is taking the electrons away from the carbon. So let's add some instructions. The question isn't asking us to provide instructions. The question just says, give me an answer. Okay? And I highly object to that. What you should be thinking is, how is this happening? Why is this happening? Because if you understand that, we can throw any structure at you and you can make predictions. If it just comes down to, oh, it just happens, you have to memorize it, which means you have to predict everything I could possibly ever ask. That's not going to work. Okay, that is a failure of a class. Okay, so oxygen being more electronegative than the carbon is doing what to the electrons in those bonds? Taking them. Cool. As it takes those electrons, we can say we're going to take the electrons in that bond. It's only taking one at a time. It can only take one bond. We can't do multiple bonds at the same time. As it takes those electrons, what starts to happen to the oxygen? It becomes more negative. It isn't formally negative yet, so we could say that's partially negative with our little delta notation. What happened to the carbon? It's partially positive. Now let's just push this to the extreme. The oxygen says, F you, I'm taking all the electrons. That's bad for the carbon. It's now missing its octet. So something needs to help stabilize that carbon. It lost its electrons. So something else needs to come in and provide electrons. Do we have something else that's providing electrons? Yeah, we got the CN. So we can take the electrons that are now on that carbon and we could share them up there. What is the result of this? What happens? There's my carbon with those methyl groups out to either end. We didn't touch those, so those are left alone. Okay? But we now have that bond to the CN, which is a problem in and of itself. Actually, the active may have fixed for us. Okay? So, CN. What's going on up the top? So I just have an oxygen up here? With a sigma bond. I didn't break one of those bonds. I kept one. I only broke one. I didn't remove those two electrons, or two pairs of electrons up at the top. Those are still there. But what I did is took that one bond, and I turned that into a lone pair up top. I've provided instructions on the left so that I would know what happened to draw the product on the right. Okay? To Sophia's question, what's a not positive or a not proton? What did this carbon donate its electrons to? Another carbon. Is that a proton? No. What did the Cn minus act as? It acts as a nucleophile because it's donating its electrons to something that is not a hydrogen. It is therefore a nucleophile. What is the carbon in our top structure? An electrophile. It is accepting electrons from a nucleophile, and the thing that is accepting electrons is not a hydrogen. It is therefore an electrophile. Does that answer your question a little bit? You can say no, that's fine. So go back to what your question was. Because what I thought I heard was, what could it donate electrons to that's not a proton? So what is a proton? And that, I'm not trying to be snarky. That's a challenging question because we have different definitions of it. We talked through it, that doesn't mean it's stuck. What is a proton? Where would I find a proton? In the nucleus. That's not the proton we're talking about. That's why it's a trash definition to call it a proton. The proton is not a nuclear proton. What is the proton we're talking about? A hydrogen ion. An acid, when we say an acid is a proton donor, it's not donating nuclear protons. It's donating hydrogen ions. What is a hydrogen ion? Well, what makes a hydrogen atom? One proton. So when we're talking about donating protons, it's not nuclear. We're putting a hydrogen atom nearby. That's all that it is. But that hydrogen atom is only a proton. So why can't we call it a proton? We can. It's just confusing because now we start thinking we're doing nuclear. We're not doing nuclear. It's just a hydrogen atom is now chilling next to the thing. That's it. Does that help?
Yeah.
So when we say not a proton, is that a hydrogen? No. Therefore, this isn't an acid. It doesn't make sense to reference this according to the acid definition. Kind of, sort of?
Yeah. So that's why it's acid-based, because inside...
This is why within the question is giving us a hint, and it's now saying Lewis acid-base. It's saying, don't mess with any hydrogens. Why? Because could you? Yes, don't. Don't worry about it. We'll worry about that in 6 weeks. Okay, because we should eventually get there, but 6 weeks. Okay? They're trying to tell you just do the simple quote-unquote chemistry. Find the most positive, find the most negative, and connect them. Okay? And the vast majority of the time, that's all you need to do. You find the most positive, you find the most negative, you connect them, and done. Okay? And what we will find through most of this semester is that works. It's lovely. Okay? One of the things that becomes challenging is what defines positive, what defines negative. Okay? That will become a little bit more challenging, and there's some questions that kind of push to that, because now you're looking at nuances of reactivity. This is why you're supposed to watch that reactivity video, because it's giving you a rule set by which you can compare different positives and different negatives. That's how you differentiate which one is more, which one is less. Why is that important? What's the most reactive one? The more positive or the less positive? The more positive. The larger your charge is, the more likely it reacts. Okay? So, back to this question. If you drew this into smart work or active, are you correct?
Yeah, I got it.
I'm going to argue, no, you are not. If that's what you drew into active, you got it wrong. Okay, what's that? You're getting it wrong?
Yeah.
Yeah. Because I didn't say I was done. What's wrong with it? Say that again? Charges. When we go through to draw our Lewis structures, remember all the way back when we drew out Lewis structures, we said as we draw them out, the last thing we have to count for is formal charges. When you draw out products, guess what you also have to do? Worry about formal charges. Okay? You can do that through calculations. You can do that through memorization. You can do that through the application of your curved arrows. Okay? Look at the things that change. Should I be looking at formal charge on that carbon or that carbon? No. Should I be looking at that oxygen? Yes, that carbon. Yes, I should look at it. That carbon. Yes. Okay, those three atoms, yes, I should absolutely be looking at. Because those three atoms changed something about reactant to product. What happened to our oxygen? What did it start as? Neutral. What does this arrow mean? It has gained electrons. If I start neutral and gain electrons, what happens? I become negatively charged. That needs to be shown as a negative oxygen. What happened to the carbon in the middle? Ooh, it just lost electrons. Should I be showing it as positive? When I'm only considering that purple arrow, yes, it is positive. Am I only considering that purple arrow? No, because the result shows that this blue arrow is also involved. So I have lost electrons and gained electrons, which means the net was no change. What was its charge? Neutral, which means my answer is neutral. Make sense? Carbon started negative. What does this arrow mean? It has lost electrons. So if it starts negative and it loses electrons, it should become neutral. Okay? Because electrons are negative. So we should see that as neutral. That is a much better answer to whether or not active accepts that is going to come down to some of the drawing stuff that I'm not familiar with, and that's what I would need to pull up. You're just like submitting every time I draw it. You don't even give me a second. Did you really submit it already? God, give me a second, man. Let me breathe. Okay? So cool. We've got that basic setup, but we do have kind of an issue. Okay? And this is where I wanted to see what was in the drawing template. What the heck is CN? Carbon bonded to nitrogen. Okay, so let's draw that out. If I draw a carbon bonded to a nitrogen, am I going to have a problem with that?
I'm going to assume that there's two H's.
Okay, I need to assume there's two H's. Where do I want to assume those two H's? On that carbon. Okay. Why do you want to assume those two H's?
Just to satisfy the octet.
Satisfy the octet. Okay. If those two H's are there, what should I see over here? Two H's. Were they here? No. Written as a formula, you don't imply hydrogens in a formula. You can imply hydrogens in a structure. Absolutely. Can't imply them in a formula. So are the two H's there? No. Okay. On top of which, let's just say for giggles you did. What about the nitrogen? Does the nitrogen have its octet? No. So that means it's not just two H's. I would also have to satisfy all those H's. Oh, dang. Okay, that's problematic. So what's going on here? The formula tells us that there are no hydrogens. I should have just erased it. Oh my goodness.
There should be electrons.
Yeah, we need more electrons. How do I get more electrons? Lone pairs. Okay, where do you want to put your lone pairs? What atom do you think is most important to address the lone pairs on? Why carbon?
Nitrogen.
Why do you guys want to say nitrogen? Oh, you're calling her out. Electronegativity. I would argue the nitrogen's more important because nitrogen's more electronegative. We should be addressing the electrons on the nitrogen first. So cool, we could add our lone pairs to the nitrogen, so now it has its octet. The problem with that is the carbon's still missing its octet. How can we ensure that the nitrogen and the carbon still have access to those electrons?
You need a triple bond.
I need a triple bond. Okay. Is this something you're supposed to know? Yeah, sorry. Okay. Where would it be easier to track? Trying to track it in the product is not the easiest place to track it. The easiest place to track it would be back in the reactant. We know we're looking at CN minus. So we could go through and draw a Lewis structure. Carbon has how many electrons? Valence? 4. Nitrogen has. As I wrote it backwards, the charge means I need to add 1, which means I need 10 electrons. Carbon, nitrogen, 2, 4, 6, 8, 10. Make a bond. My carbon's missing its octet. What happens? I make the triple bond. Come on, line. There it is. Which of those atoms is negatively charged, the carbon or the nitrogen? Turns out it's the carbon, and the carbon is the one that's negative. That's why we drew the carbon negative here. Were you responsible for knowing all of that? Yeah, that goes back to the Lewis structure stuff and the familiarity with those structures. This is why that initial stuff with Lewis structures is so important, to pick up those common bonding patterns so that you can quickly evaluate these things. See how we get a massive leap in difficulty if we don't do those things to begin with. Okay? So, within this, what I was hoping to see when drawing this out it doesn't let me draw it where I want to draw it. I've got my O negative. Sorry, it's a little small. But that was the O negative, and then I need this one to be a CN. They do have a CN.
See, the other day, I swear to God that they didn't. Like, I was like, how
This CN is problematic, though. Why is this CN problem? Whoa.
It's right next to the O.
You dipped. Oh, no, see, there it is. It was there. Sorry. And maybe they didn't, I don't know. What I would argue, or not argue, but the way that you could do it would be like, well, if it's CN and I need a triple bond, I'll do the triple. Yeah, it's just playing with geometry on me.
I tried that too.
Yeah. And there we go. There's the C, the triple bond N.
Yeah.
Here,
It wants a little.
include lone pairs. God, really? Why didn't you call attention to that at the very beginning, you silly program? Okay, I got it. Oh, and then the nitrogen. No, I didn't want that. Go away. Do I do this?
Yeah.
Okay, I need the nitrogen with a lone pair. See, it's intuitive. Don't you just get it?
I get it now.
And theoretically now when we submit, it's just that I can say it was correct. Okay? So, is it important to know all those lone pairs are there? Yes. The lone pairs was what allowed us to do the chemistry for that reaction, since it looks like you're looking at it, Lena. Give me a sec. So that you can now predict the instructions. This is where I want the things to go so that you can draw products. So it's very important to have those lone pairs. Do you really want your homework system grading you on the presence of those lone pairs? Probably not, but now you're saying they're important enough that I need them to figure out the answer, but not important enough that I should have to show them. Sorry, you can't have it both ways. Okay? Which means you will have to struggle with dealing with the lone pairs. I fully sympathize with that. You do got to watch out for it. And yes, it will burn you in many a case. And if you feel like you're getting burned in too many places, let me know. And I can try and adjust on the homework. On exams, generally I care less. But on the homework, the intent is to be perfect so that you know where those things are. As frustrating as that is. Does that work?
Mm-hmm.
So that hopefully addresses the not hydrogen, and it addresses one of our homework questions on how we're connecting those pieces. Okay? If we were to continue back with our slideshow, we've got those acids, strong and not. Theoretically, depending on your instructor, you may have been asked to memorize or at least be familiar with your strong acids. That's pretty borderline. Most instructors I've noticed don't seem to require it. Okay, but you should know those are all pretty strong acids. Generally speaking, if you recognize it as an acid, it was probably a strong acid, H2Cl, H2SO4, to a lesser extent, maybe nitric acid. You've probably memorized those already. If you haven't, it's useful to memorize them. The iodide and the bromide, we can actually derive if we know HCl is a strong acid. And we'll look at that in a second, which gets to our reactivity. The weak acids are now ranked based on the stability. Okay, we're looking at the stability of that process. If we're talking about two acids, let's pick one. Let's call it HA red, A for acid, yeah, see, I'm super creative, and HA purple. And I want to see which of these is the stronger acid. Well, if it's a stronger acid, what is it producing more of? What does my acid produce? H plus. So the stronger acid is going to produce more H plus. What does that mean? That means this arrow goes more to making more product. Okay? And this does bring in a little bit the idea of our equilibrium. Our reactions are reversible. This could revert backwards. Okay? And if I set it up in this scenario with that arrow, which acid is the stronger acid? The red one or the purple one? The purple one. Because what does the red one do? It takes some of that HA or that H plus and turns it back into HA. So I have less H plus. Okay? So the arrow could provide that context. What if I did this? Which is the stronger acid? Red or purple? Okay, your suggestion is neither. Why neither? They're both going backwards and forwards. Does anybody else want to challenge that a little bit?
Would it be red?
Why do you want to say red?
Only because the purple air or the black arrow under the purple one's larger?
Yeah, we look at the purple one and go, oh, it's a larger arrow. Which may seem a bit silly, but yeah, that's how we kind of define it, is we look at the size of the arrow to dictate that. Okay? That's only dictated because we know the answer. What if we don't know the answer? Okay? That not knowing the answer is now getting into trying to decide how would we rank these, looking at our weak acids. Okay? Well, I want the one that produces the most H+. If I look at the presence of H+, that's not going to be helpful though. Because I see H+ here, and what do I see here? H+. There is no difference between them. The only place I see a difference is either at the beginning, the HAs, or at the end, the A minuses. Okay? Which one do you think might be easier for me to think about if we consider how we've looked at organic chemistry so far?
A minuses.
Why A minuses?
Because they're separated by themselves. Because they're charged.
That's where I would go. It's easier to look at the A minuses, not just because they're charged, it's because they are negatively charged, which means what do they have? Electrons. And what do we talk about in all of OChem? Electrons. Where are the electrons?
On that.
Okay? That was somewhat rhetorical. Apologize for that. Okay? That's what we care about. Where are my electrons located? And if A minus purple stabilizes those negative electrons better than red, what does that mean? That means purple A forms more. If purple A forms more than red A, what does that mean about the H+? If I get more purple A than red A, what does that mean about my purple H+ versus red H+? You don't have to worry about attach. I have more of this than I have of this. What does that mean happens with the amount of H plus? It's just more. Where did the A minus come from? It came from HA by losing H plus. If I have more purple than I have red, what happens? I get more purple H. That's a necessary byproduct of it. So what I want to see is how can I make that more stable? Because the more stable it becomes, the less likely it wants to react backwards. It becomes a smaller negative. Well, what dictates stability? Okay, well, there's a couple things we do. Let's pick out some specifics. Let's go through and call this H2O, and let's look at H3O plus. So we've got HOH, H2O, and H3O plus. Which of those do you think is the stronger acid? Just giving it. Everything else gone. H3O plus. Why do you think H3O plus is a stronger acid?
It has one more hydrogen.
One more hydrogen. Okay, that's an interesting statement. Fair. Turns out the amount of hydrogens is irrelevant because how many hydrogens can be gotten rid of at any given time? One. That's it. So I don't care how many are present. I care about the reactivity of those. Okay? Why did I pick H3O plus? What happens when you react acid with H2O? What do you get? H3O plus. H3O plus is one of those common, this is an acid things. Okay? Just because you didn't remember that is okay, don't stress. Okay, what happens? H2O gets rid of H plus. So I don't have A minus anymore. What do I have out here? Bingo. Half bingo. OH minus. Okay? I don't have H3O plus out here for A minus now. For the purple, what do I have? H2O. Which is more stable, OH minus or H2O? H2O. Why? It's neutral, whereas OH minus is charged. Which one of these is the stronger acid, H3O plus or H2O? Which one produces the most product? Purple or red? Purple. It produced the more stable species than this one.
So it's more stable means stronger.
And this one we gotta be careful. More stable what?
Charge.
Is this more stable than that? No. H3O plus is less stable than H2O. So your more stable statement I'm going to challenge because that's not clear. More stable product. That gets a little bit better. Okay, the more stable product is the stronger acid. Okay, but what if I now switch and look at bases? Because I have acids and I have bases. So what if I switch the definition to bases? The more stable product as well? This gets weird. Okay, what we're referencing isn't necessarily the more stable product. What we're referencing is the particular species that we care about. When we're looking at our acids, what we're comparing is the stability of the conjugate base. This removes the concept of product and reactant. What we want is our conjugate base. Our conjugate base is going to be this species, okay, kind of by definition. So that means when we look at a chemical reaction, we have to be able to say that this is an acid which produces my conjugate base and my conjugate acid, and this becomes problematic with that one. Okay, what's happening with these? Well, to reverse the reaction, what do we have? Well, this species acts as an acid because it's H plus. This species acts as a base because it's the electron source. Okay, so when we're ranking acidity, what we're looking at is the stability of the conjugate base. So we start with our acid and I say, well, what does it look like if it removes a hydrogen and I look at the conjugate base? I care about the conjugate base because that's where I can see electrons. That's where I could see a potential for charge. I don't look at my starting acids because in my starting acids, typically what charge would I see if I saw any charge? Positive. And what is a positive charge? Missing electrons. Well, all of OChem is where the hell are all electrons? Missing electrons is confusing. I don't want to look at negatives. That's why we look to the conjugate base. Kind of, sort of. What if we switch this? Should we switch it? Let's not switch it. I said there was something you could derive. What am I going to try and erase? Let's just erase it all. I said if you knew HCl, you could know HBr as well. And for that matter, HI. Those are both acids. Which one is the stronger acid? Like we already said they were strong. Just because we have strong people doesn't mean there's stronger people even within that. This is why you get the world's strongest person. Like you go through competitions, you still get stronger people within that. Which one is stronger, HBr or HCl? How do we figure it out? How do we figure out the stronger acid? What do we need to look at? We need to look at what? Products. And I said I didn't like products. What did I want to hear instead? I want to look at the conjugate base. So these are going to go through a chemical reaction. That chemical reaction is going to produce H plus in both cases and the conjugate base, Br minus and Cl minus. I want to now evaluate the stability of those two things. Well, the first thing I would look for would be, no, because we didn't look at electronegativity with our previous example. Our previous example, what do we look for? Charge. We would start with charge. Are they both charged? Yes. That's why we can now move on to something else. Well, now the question becomes is what is that something else that's different between bromine and chlorine? Okay, we heard a difference. Bromine is less electronegative. If we look at our electronegativity, than chlorine. Is that the only difference between bromine and chlorine?
Size.
Ooh, there's also a size. How does that change?
Bromine is bigger.
Bromine is bigger than chlorine. Okay. If we look at electronegativity, right, which would we expect to be more stable, Cl minus or Br minus? Cl minus because more electronegativity. And that's the ability to hold electrons. That makes sense. Cl minus. I completely agree. What if we look at size? That's a harder one to think through. How do we decide which one is more stable?
Who has more space for the electrons?
You're digging into the video a little bit. That's okay. What makes them both reactive? Why are they charged?
They're halogens.
Why are they charged? Go back to where we had Br minus and Cl minus. Why do we have Br minus? Why do we have Cl minus? What happened?
They got rid of H.
There's our description. They stole electrons from the bond. Okay? So what makes them reactive? Yes, they are charged. Why are they charged? They are charged because they have gained an electron. So when we're looking at Br negative and Cl negative, they are reactive because they have an extra electron. Ta-da! Ta-da! The electron's the same in both cases. Really? It's just a question of where can that electron exist. The electron in bromine can exist in a larger area. The electron in the chlorine can exist in a smaller area. How does this contribute to reactivity? When does it react?
When it interacts with H.
What's it?
When either of them is bromine. Oh, the electron.
The electron in the bromine or the chlorine interacts with something else. So what we're talking about is if I want it to interact with me, I have to stick my finger in and I have to touch the electron. Right? Now it's interacting, now I can make a bond. Which one of these is going to allow me to make a bond faster? Chlorine, because it's smaller. The odds of me hitting that electron in that space, much higher odds, which means the chlorine is more reactive, which means the bromine is more stable, which means
That's a stronger.
HBr is a stronger acid. Why is that problematic? You got to rewind 5 minutes. When we looked at the electronegativity, it said the HCl was the stronger acid. So we get an issue here. Size versus electronegativity. They lead to differing results or differing conclusions. We would have to know which one was more important. How do we know which one's more important? Memorize only works if you know what the answer is. How do we know what the answer is? We test it. We go into the lab, we test it. We say, which one of these is the stronger acid? Guess which one's the stronger acid? HBr. If HBr is the stronger acid, which is more important, size or electronegativity? Size. So now when we're starting to think through ranking our acidities, we look at our conjugate bases. And we'll start by looking at charge. Then we can look at size. Then we can look at electronegativity. Awesome. We're creating a ranking system that allows us to evaluate those differences. That's pretty cool. And that's what we did. We test this a whole bunch of times, and we found those systems. We could go in and we could quantify the bejesus out of it. We don't want to do that. That's math. Just leave that to somebody else. What we care about is what was the end result. The end result gave us this ranking system that allowed us to evaluate, and with that evaluation, we can now make these predictions. That's cool. Kinda, sorta? So how do we use that? Okay, well, we're going to use it in a couple ways. First and foremost, what we just started evaluating was, ta-da, this god-awful, painful thing that everybody hates and doesn't like to apply. This is what you need to use every time. Every time you run a reaction, you start, where's the charge thing? Why? Because that's the most important thing. If I got charge, that's my chemistry. If I don't have charge, what's the next thing I need to move to? I need to see, are there size effects? Are there size things that are going to dictate my reactivity? Then I'll look at electronegativity. All of those are very centrally located. Right? That's just the immediate issue. If we're looking at fights, is the person coming in with fists, with a knife, or with a gun? Those make different interpretations. Those are the immediate things. What's in their hand? Okay? Is it a threat? Right? Is it fists? Is it a jellyfish? Is it a knife? Okay, I have an interpretation off of that. Okay? But there are other things that would affect how you interacted with that person. If you saw somebody coming at you with just open hands, it's probably not that big a deal. If you saw them coming at you with a knife, oh, it's a kitchen, it's okay. Right? There's some secondary context. Right? What if they had a hood pulled down over their face? You couldn't see their face. You couldn't see their hands because they were embedded in the sweater. Is that going to change your response? Yeah. Okay? Well, that's now looking at secondary things. We look first at the immediate threat, what's in the hand, and then we look at those secondary threats. What are those secondary threats in organic chemistry? Well, first it's the atom. What's in the hand? Now, what's behind that hand? That's the molecular effect. The molecular effect mirrors the atom effect. When we talk about size of the atom, we look at a molecular effect as well. That's also size, but it's in quotes, because it's not just how big the atom is, because what we care about is where the electrons move. Can electrons just move wherever they want in a molecule? No, they're limited. When can they move more?
When that molecule's bigger.
No. Ooh, it does have to do with orbitals, but in particular, a particular type of orbital that allows the electrons to move. S orbital wrong, sp orbital wrong.
P orbital.
P orbitals. What are we talking about if we're talking about electrons moving through p orbitals? Pirate's favorite letter.
Oh.
R. Resonance. Oh, don't give me that, dude. Resonance becomes critical. It's not just how big the atom or the molecule is, it's does that size allow for the electrons to move? That's molecular size effects. Okay? Then we move to a molecular effect of electronegativity. That one's a little bit more straightforward. That's known as induction. Okay? And in the induction, it's just, is there an electronegative atom? If there's an electronegative atom in the molecule, what is it doing to all the electrons? Hoarding them. It draws all of the electrons in the molecule towards it. Depending on what you're looking at, that's going to change the reactivity. Okay? And then we get to this last one, which really sucks, and hopefully we never have to worry about it. Okay. Or this okay, but we'll see. Okay? This is where hybridization comes in, substitution patterns, and all sorts of other fun things that are interesting. And they're more like thought games when we talk about this class that would turn into potential problems in another class. Okay? So, ranking weak acids, these are all ranking weak acids. Do you want to try a set? Yeah? Okay, I'm going to give you, that one's too long. We'll just do those two. And I'll try and pause the video and restart it. Unpause. What's our first step for ranking our acids?
Conjugate bases.
You need to draw the conjugate base. What is an acid?
One is positive.
Donates H+. So if we're looking at the conjugate base, what do we need to do? Remove a hydrogen, and in more specifics, remove the H positive, leaving behind a negative on whatever atom had that hydrogen connected to it. I know it stinks, but we're going to go ahead and talk through them. If we talk with the H2O and HF, we remove a hydrogen, we get OH minus and F minus. So we start with charge. What's the charge on our oxygen? Negative. Charge on our fluorine? Negative. Now what's the next thing? Size. Oxygen versus fluorine. Is there a difference in size? There's not a significant one, which means move to the next thing. Electronegativity. Is there a difference in electronegativity between oxygen and fluorine? Yes. What is that difference? Fluorine is more electronegative, which means what is it doing to the electrons? Hoarding them, making F minus more stable, which then means HF is the stronger acid. We'll box our stronger acids. CH3F, CH2F2. Okay? Here we've got formulas. Formulas can be more challenging. This is why you're responsible for drawing out those structures. That's also why I deleted most of the options, is because I had a bunch of formulas and it's easier to deal with structures. So if we look at our structures, negative CH2F. Again, that's not a structure, so we can draw out a Lewis structure for it. Okay? So we've got that. For the other one, we've got that one. Okay? And we now compare those two. We start with charge. What's the charge? They're both negative. In particular, what is negative? The carbon. Okay, it is not the fluorine, because the fluorine is not the one that had the hydrogen. It was the carbon. So when I'm now looking for charge, I'm looking at the atom that's holding the charge. It's both negative. When I move to the next thing, when we're looking at size, we're looking at the atom that holds that charge. That's the important part. That's where all the chemistry happened. The atom is carbon versus carbon. Definitely no difference in size. Definitely no difference in electronegativity. Is there resonance? Okay? And in that resonance, what am I trying to do? What electrons do I want to move when I'm looking at resonance in this particular scenario? Say it again. Which lone pairs? There's lots of lone pairs. The ones on the carbon. Those are the only ones I care about. Why do I care about those electrons? That's the negative. That's what started the whole question off. So I could draw a molecule where there's tons of resonance out here. If that resonance never talks to this negative, it doesn't do anything. It's not relevant. Does that make sense? So always focus, find the atom that's reactive and try and deal with it. If we try to look at resonance, is there going to be resonance? No. And that answer should be pretty quick. That was partly what we did in Unit 1, was trying to push that resonance practice so that you're used to recognizing that there is no resonance for this or for the blue one. If there's no resonance for my red and blue, then what do I move to? Induction, okay? Which is effectively electronegativity. I'm now looking at a molecular effect. I'm looking at the atoms that are connected outside of that carbon. And I'm saying, what do those atoms do? And if I look, there's a fluorine on the red one. What is that fluorine doing to the electrons in the bond between the carbon and the fluorine?
Taking them more.
It pulls them in towards the fluorine, which means what happens to that negative charge?
Becomes less negative.
It becomes less negative. It's getting pulled into the molecule. That means that's more stable. Cool. What happened in the blue one?
It's getting pulled in two separate ways.
It's getting pulled in twice as much as it is here, which means what happens to the reactivity?
It's even less.
It's even less, which means the blue is more stable, which then means
That's the stronger acid.
the starting acid is your stronger acid. Kind of, sort of? What happens with the next two in the middle? Okay. Theoretically, these two can be dictated and ranked immediately just using our nomenclature skills, because we look at the left structure and we would recognize the functional group in that structure to be
The last structure?
a carboxylic
Carboxylic. I couldn't say it.
acid. Why do we call it a carboxylic acid?
Because it's an acid.
Because it's an acid. So there's probably a good reason to explain that one being the acid. What's the other functional group? An alcohol. One's an acid, one's not called an acid. The stronger acid is probably the one that's an acid. Why? Draw out the conjugate base. Remove the hydrogen. We remove the hydrogen. We get a negative oxygen. We get a negative oxygen. Charge, same. Atom effect, same size, same electronegativity. Now we move to resonance. Do we have a resonance option?
There's pi bond on
I can draw a resonance structure where I can take those electrons and I can share them with the top oxygen. What does that mean? This negative charge is being dispersed across more atoms. We've given it a larger space to exist. More space means
that. Less reactive.
less reactive, which means more stable, which then means the acid, our starting structure, is the stronger acid. Okay? So nearly all your ranking systems, when you go through and deal with those ranking questions, are having you look at those rules and saying, compare, compare, compare. And every time you're picking two. Even if it's got 6 things to rank, you pick 2. You order them, and then you bring in another one, and then you bring in another one, and then you bring in another one. And it takes time to work your way through it, so spend the time to slowly process out each of those steps. Okay? Kind of make sense? Okay. Believe it or not, I'm aware of time a little bit. I just want to see a little bit. If we go through and look at the rest of the slides, what we're moving into is the ranking acidity, which as you go through and compare things, this O-carb hybridization is going to appear, so it will be talked about in the play posit, and that will become relevant. Excitingly enough, today in lab. And then, I'm really nervous about that slide. I don't know I want to do that. I'll talk about the pKa's, but if we go through and look at this, do you see anything that's actually new slides?
No.
All of this is videos that you should already be watching. There's really only 2 slides left. And I know I am slow, but I'm pretty sure I can cover 2 slides on Thursday, which would suggest the exam should be next week. genuinely feel that content that's being addressed here is vastly more important than getting into chemical reactions. I want you to have practice looking at identifying reactions. I want you to have practice looking at all the different mechanistic steps and being able to say, that is this mechanism, that is this mechanism, that is this mechanism. Even though the slide content isn't there, I don't feel like we would have enough practice before an exam next Thursday. So I would like to push the exam for the following week. Since Sophia seems to think that's a good idea, we'll go ahead and do the exam next week. We'll do it in 2 weeks. We okay with that?
Yes, yes.
Okay. What I will point out is a couple things. First thing, come on, fucking baby names, organic name. Stupid. What I'm gonna effectively do on this Thursday and next week, believe it or not, is a couple things. One, I will answer what questions you guys have about these videos. Okay? These videos are not particularly easy. There's a lot of content moving through them. We're looking at how reactions change around. We just talked about acid and base. That's the transfer of hydrogen only. But then we get 4 other reaction types. You need to be able to look at a reaction and be like, boom, that's elimination. Boom, that's addition. That's substitution. That's the what the hell is that? I don't know what that is. Let's call it radical and move on. Okay? You need that fluidity. That is vastly more important than saying, oh, when I add H2, it does this, which is the next unit. Here's a reagent, here's what it does. Here's a reagent, here's what it does. So I want you to be able to look at those reagents or those reactions and say, this is what they are applying. These are the complications I would have to worry about on them, which means it's really, really important to be able to look at reactions and mechanistic steps to say what's happening and changing. So what those class periods will be is effectively answering your questions, and then what I'm going to do is pull up this thing, which I'm notorious for hating these, but these are all the named reactions that someone decided that they got to stamp a name on, and what we'll do is we'll just click one. We'll open it up, we'll look at that reaction and say what happened. Is that acid base? Is that addition? Is that elimination? Okay? And we want to be able to look at those pieces to identify it. We'll then, if we're lucky, scroll down and they'll give us a mechanism. And we'll say, okay, what's happening in that mechanism? That's acid base. That's an SN2. That's heterolysis. Okay? So identifying those changes. Part of that is also going to be you just finding, I would recommend, just Google named reactions, okay? Because you don't need to be right, which is going to be the other challenging thing here. You look to the textbook, it's going to be hard to find things. You're just looking at a reaction, and I want you to take a step back from, oh my God, all the things that are happening. But you could take something that is a mechanistic step where they're showing curved arrows, cover the product, draw what you think the product's supposed to be. Now you can check your work immediately underneath. Okay? It's going to be harder, but you can find them where you're given a reactant and a product of a mechanistic step where they haven't given you curved arrows. Draw curved arrows. Add the instructions to get from reactant to product. That one becomes harder because you have to make sure you're looking at a mechanistic step. Up here, if you tried to add curved arrows to do that reaction, you're going to be lost. Okay? Because that's not a mechanistic step. That's a chemical reaction. How do I know the level of complexity behind what things are changing within it? Okay? You aren't quite there yet, though I would expect you to get there. With that, I do have to stop. I know I said I was paying attention to time, and then I talked for 5 minutes.